Hi everyone, this is the part 2 of carbohydrates, and in this video we are going to discuss about the structures of glucose and fructose. So let's get started. D and L designation in the name of a compound. You may have observed that there are so many compounds that are present and that differs in their spatial arrangement, and those compounds are known as stereoisomers, which we have discussed in our previous video also. And these stereoisomers may have letters D and L before their name. Now, what does that mean? The letters D and L basically represent the configuration of that stereoisomer. The word relative means comparison. So, when we assign DLN configuration to a compound, we compare the configuration of that compound with a fixed other compound, and that other compound is glyceraldehyde. दैट मीन्स अगर किसी भी कंपाउंड के आगे हम डी और एल असाइन करते हैं तो हम ग्लिसरल्डिहाइड की कॉन्फ़िगरेशन के रेफरेंस में करते हैं. Hence, glyceraldehyde is also called as reference molecule of biochemistry because this is the molecule that we use to assign different configurations to a stereoisomer. Now we have to know that why we have chosen glyceraldehyde as a reference molecule. Glyceraldehyde contains one asymmetric carbon atom. It means it contains one chiral atom. Chiral atom is the atom which has four different functional groups attached to it. You can see here this carbon has one aldehyde group, one hydrogen atom, one hydroxide and one alcohol atom or molecule. Now if we take the mirror image of this compound, it will form this molecule where you can see the OH comes in front of this OH molecule. So we can see that this forms two enantiomeric forms. First, in which OH is present on the right side, and the second in which OH is present on the left side. So when in a compound the OH group is present on the right side, that compound gets the configuration D. So the name of the compound becomes D-glyceraldehyde, and when the OH is present on the left hand side, then it gets the letter D and it forms configuration L-glyceraldehyde. And you have to remember here that D and L letters have no relation with the optical activity of the compound. इट मीन्स डी एंड एल कॉन्फ़िगरेशन असाइन करने पर किसी भी कंपाउंड को हमें ये नहीं पता लगेगा कि ऑप्टिकल एक्टिविटी कौन सी डायरेक्शन में हो रही है, वेदर इट इज इन द राइट डायरेक्शन और इट इज इन द लेफ्ट डायरेक्शन. The optical activity is just shown by the chiral carbon atom. So if in a compound a chiral carbon atom is present and there is no symmetry in that compound, then the optical activity of that compound will be shown. अब हमें पता है कि हमारा रेफरेंस मॉलिक्यूल ग्लिसरल्डिहाइड है, तो बाकी के सारे जितने भी मॉलिक्यूल्स होते हैं, अगर हमें उनमें डी और एल कॉन्फ़िगरेशन असाइन करनी है, दैट वी विल असाइन विद रेफरेंस टू दिस मॉलिक्यूल विच इज ग्लिसरल्डिहाइड. लेट्स टेक एन एग्जांपल ग्लूकोज. ग्लूकोज में यहाँ पर 6 कार्बन एटम्स हैं और हमारे जो कायरल एटम्स हैं वो 4 हैं, 1 2 3 4. अब इनमें से कैसे पता चलेगा हमें कि हमें कौन से कार्बन के अलोंग कॉन्फ़िगरेशन को चेक करना है. सो वी हैव टू टेक द लोएस्ट asymmetric carbon atom. You can see this is CH2OH. So this carbon just above it is the lowest carbon atom for glucose. So if OH is on the right hand side, then this molecule is comparable, or we can refer to D-glyceraldehyde in comparison to this glucose, and then the configuration along this glucose will be D. And in the another molecule we can see, which is the mirror image of this molecule, the OH atom on the last asymmetric carbon is on the left side, hence it will be comparable to the L-glyceraldehyde, and this glucose will also get the configuration L and will be called as L-glucose. How we assign the plus and minus configuration to isomers? तो इसमें सबसे पहले हमें बात ये ध्यान में रखनी है कि प्लस एंड माइनस कॉन्फ़िगरेशन जब हम किसी भी एक कंपाउंड को असाइन करते हैं तो वो एक्सपेरिमेंट के थ्रू करते हैं. By just looking at the compound, we cannot assign plus and minus configuration to a compound. That is, it is an experimental value, and while doing the experiment, if any compound rotates the plane polarized light to right direction or to clockwise direction, then that compound is known as dextrorotatory compound, and that compound is assigned plus configuration. And on the contrary, the compound which rotates the plane polarized light to left direction or in anti-clockwise direction, it is called as levorotatory compound and assigned minus configuration. Again, taking the example of glucose, here D is written in this glucose. That means the OH group present on the last asymmetric carbon atom is on the right side. You have to remember that we have to consider the last asymmetric carbon atom and not the last carbon atom. Carbon 6 is the last carbon atom, but carbon 5 is the last or lowest asymmetric carbon atom. That means it is attached to 4 different groups. So if the OH is on the right side, then D configuration is assigned. So when this molecule is being put into experiment, then this rotates the plane polarized light to the right direction or clockwise direction. Hence, it is assigned plus configuration. So this is D plus glucose. Whereas for the fructose, D fructose, because the OH group present on the last asymmetric carbon atom is on the right side, and when this compound is been put into experiment, it rotates the plane polarized light to the left direction or anti-clockwise direction. Hence it is assigned as minus configuration and it becomes D minus fructose. And you have to make a note that D and L letters have no relation with the optical activity of the compound. That is, it has no relation with plus and minus, because plus and minus is assigned to a compound based on the experiment, whereas D and N configuration is assigned to a compound based on its structures. While performing reactions with glucose, there are some reactions which do not occur. For example, Schiff's test और 2,4-DNP टेस्ट. ये दोनों जो टेस्ट होते हैं ये एल्डिहाइड ग्रुप के लिए होते हैं, और अगर हमें ग्लूकोज के स्ट्रक्चर को देखें देन वी कैन सी दिस फ्री एल्डिहाइड ग्रुप विच इज प्रेजेंट. तो ये दोनों हमारे जो टेस्ट होते हैं ये अकर होने चाहिए. सिमिलरली एडिशन प्रोडक्ट भी हमें NaHCO3 के साथ मिलना चाहिए, और ग्रिग्नार्ड रिएजेंट के साथ भी ग्लूकोज अगर रिएक्ट करे तो उसके साथ भी एक प्रोडक्ट मिलना चाहिए. लेकिन ये सारे रिएक्शंस और टेस्ट जो होते हैं ये हमें नहीं मिलते, या फिर ये रिएक्शंस अकर नहीं होते. एंड ऑल्सो ग्लूकोज पेंटाएसिटेट doesn't react with hydroxylamine, which indicates the absence of free CHO group. That means all these reactions indicate that in glucose the free CHO group or free aldehyde group is absent. और हमने प्रीवियस स्लाइड्स में देखा कि ग्लूकोज का स्ट्रक्चर ऐसा होता है, बट यहाँ पर हमने देखा कि हमें फ्री aldehyde ग्रुप का कोई भी रिएक्शन नहीं मिल रहा. That means the glucose is present in its cyclic form and not in its open structure. Now we will see what happens in the cyclic structure of the glucose, due to which the free aldehydic group or open chain structure reactions are not shown by glucose. As you can see, this is the open chain structure of glucose. So when this glucose is put into a solution, the proton or H plus of that solution attacks the oxygen atom of aldehydic group. This is because oxygen is rich in electrons, and moreover oxygen is electronegative atom, so it attracts the shared pair of electron towards itself. And due to this, oxygen gets minus charge and carbon gets positive charge, and it becomes electrophilic center. So what happens is that the OH group, which is present on the fifth carbon atom, it reacts or it attacks the carbon atom of aldehydic group, and this forms the cyclic structure of the glucose. Now there are two ways in which this OH group attacks at the carbon atom. If the OH group attacks from upwards, then it pushes the OH atom downwards and it comes on the right side. And the structure looks like this. The first carbon atom is bonded to the fifth carbon atom through O, which is oxygen atom. And rest of the configuration along the other carbon atoms remain same. And this structure is known as alpha D plus glucopyranose. And on the other side, if OH group reacts or attacks from downwards, then it pushes the OH group upwards, and in this projection it is written on the left side, and the rest configuration on the other carbon atoms remain same, and it is assigned as B beta configuration, and the name becomes beta D plus glucopyranose. And this is known as Fischer projection. Fischer projection is basically a 2D representation of a 3D molecule. Hence, in the cyclic structure of glucose, if OH is present on the right side, then it is assigned as alpha configuration, and if OH is present on the left side, then it is assigned as beta configuration. And how we name these two compounds, we will learn that in the next slide. To name the cyclic structures, we have to know about two types of heterocyclic ring, and for that, first we have to understand what are heterocyclic ring. So if in a ring there are two types of atoms present, then it is known as heterocyclic ring. For example, here oxygen atom is present and at the rest positions carbon atoms are present. So in this ring two types of atoms are present. So this ring is heterocyclic ring, and if it is a 5-membered ring having oxygen atom in it, then it is termed as furan ring. On the other hand, if we have a 6-membered ring having oxygen atom in that ring, then it is known as pyran ring. You can see there are two types of different atom present in this ring also. Here is the oxygen atom, and at the rest of the position carbon atoms are present. So this is the open chain structure of glucose, and the OH group which is present on C5 attacks the C1, and this forms the cyclic structure of the glucose, and there exist two cyclic forms. While making 3D projection of cyclic structure, which is also called as Hayward projection, we have to remember that while making the ring, we have to assign carbons the position in the clockwise direction. This is carbon 1, then carbon 2, carbon 3, carbon 4, carbon 5, and then the carbon 6. And while assigning the group, we have to remember that the group which is present on the right side in the open chain structure comes at the downward position, and the group which is present on the left side in the open chain structure comes at the upward position in the cyclic structure. So when the OH group attacks from upwards, the new OH group which is formed at carbon 1 comes at the right hand side in the Fisher projection, which is 2D projection, and hence when it is made in 3D form it comes at the downward position. And when the OH attacks from downwards, the OH formed at C1 comes at the left hand side in 2D form, and while making it in 3D form it comes at the upward position. All other groups are attached in the similar way. Hence in 3D when OH is at carbon 1 it is in the downward position and it gets alpha configuration. And in 3D when OH group present on the carbon 1 comes at the upward position, it gets the configuration beta. Glucose is a D series compound because the OH group which is present on the lowest asymmetric carbon atom is present on the right hand side, and these get plus configuration because both of these compounds rotate the plane polarized light into the clockwise direction or into right direction. Glucopyranose. Now we know that the six-membered ring which contains one heteroatom is known as pyranose. So here the heteroatom is oxygen. So the name of both of these compounds is glucopyranose. And when the OH group is present in the downward direction, it gets alpha configuration. And when the OH group is present on the upward direction, it gets beta configuration. And the 3D representation of both of these cyclic structures is named as Haworth projection. Both of these structures are similar, but it is just that their configuration about carbon 1 is only different. So the isomers which differ only about configuration at one carbon are called anomers. So both of these are anomers. And what are anomers? It means that they show different optical activities because they differ only at one carbon. Hence glucose has two anomers, which is first is alpha form and the second is beta form. So when glucose is put into a solution, the three forms, which is open chain form, alpha form and beta form, all exist in an equilibrium. Alpha form has angle of rotation of about 111 degrees and the beta form has the angle of rotation of about 19.2 degrees. So alpha form interchange into beta form through an open chain intermediate, and hence the net optical rotation of that solution comes out to be 52.5 degrees. So this process or this spontaneous change in the angle of rotation of an optically active compound which comes when it is put into a solution is called mutarotation. Glucose show mutarotation because the alpha form interchange into beta form through an open chain intermediate. Now we will talk about fructose. Fructose has a ketonic group and it has 6 carbon atoms. Therefore, it is classified as a ketohexose compound. And since the OH group, which is present on the lowest asymmetric carbon atom, is present on the right side, we can say that this compound belongs to D series. It rotates the plane polarized light into anti-clockwise or in left direction, so it is called as a levorotatory compound, and it gets the minus configuration. Now, just like glucose, fructose also form the cyclic structure, but here the OH group which is present on C5 attacks C2 rather than C1, and thus two forms are formed. When these OH groups attack from the upwards, the OH group formed at C2 comes in the right direction, and when the OH of C5 attacks C2 from downwards, the OH group so formed at C2 comes in the left direction. And when the OH group is on the right side, it gets alpha configuration. And when the OH is on the left side, it gets beta configuration. Hence, this is alpha D minus fructofuranose. Furan is the ring when it is a 5-membered ring with oxygen atom in between. And this structure gets the name beta D minus fructofuranose. These are the Fischer projection, which is a 2D representation of a 3D molecule. And these are the 3D forms of the cyclic structures that are formed by D-fructose. That is, when they undergo cyclization, they form two structures, which is alpha form and beta form. And you can see the OH group is present in the downward direction at alpha form, and the OH group is present on the upward direction in beta form. And these are known as the Haworth projection. And both of these molecules, which is alpha D fructofuranose and beta D fructofuranose, undergo mutarotation, which is the spontaneous change in their optical activity when they are put into a solution. I will be covering up disaccharides and polysaccharides in the next video. If you have any doubt, you can ask in the comment section. Till then, keep trying.